Derivatives of trigonometric functions. Today's objectives: evaluate limits of specific functions that involve the subject called trigonometry. Take derivatives of trigonometric functions, right? We're using rules of differentiation to expand our knowledge of functions, and that includes trigonometric functions. And of course, if we have time, we're going to continue to use product and quotient rules to find more derivative functions. Like I said, we're just going to expand our knowledge of functions. Some warm-up from algebra and trig is, if you notice from your prior algebra and trig experience, it will make things a little bit easier to understand. We're going to start with three major theorems here. They all involve trigonometric functions, and they're actually limits, okay? Each of these is actually its own identity. And we'll concentrate on proving one of these, and I'll leave it as an exercise or practice to prove the second two. We're going to concentrate on this first proof here that definitely involves prior experience or pre-calculus experience. And we will execute the squeeze theorem to conclude that identity. The first thing you want to do is consider a small angle. Well, what do I mean by small angle here? I really mean a 90-degree or less angle. Remember, we also need to know radians. So in calculus, we concentrate on radians. When we write angles in terms of pi, it is assumed that this is actually in radians. So we write theta to be less than pi over 2 radians, and it's also going to be representing a section of a unit circle. So if you look at the diagram here, you can see theta is less than 90 degrees or less than pi over 2 radians. And it's also a section of the unit circle. So you can see a radius of 1 there and a radius of 1 here. Now notice the measure of the line segment BC is less than the measure of the line segment BA. Now the measure of the line segment BA is definitely less than the measure of the arc of BA. We know this because the shortest distance between any 2 points is a straight line. So this arc must be a longer distance. Now what is the measurement of BC? The measurement of BC is simply sine of theta. Sine of theta is going to be opposite over hypotenuse. So yes, your trigonometric experience is very important in the study of calculus. Let's look at the arc of BA again. The arc of BA is really from the arc formula from trigonometry. So the arc of BA is simply a result of the arc formula where r is actually just 1. And this is because we are in part of a unit circle. So the arc of BA here is just theta radians. So this right here is measured in radians. And one more thing, we need to look at the tangent of theta. Well, tangent of theta, you can see a big triangle here. And you know this side is 1. So when you take the tangent of theta, it's going to be opposite over adjacent. But the adjacent is just the length 1. So tangent of theta is actually just the measure of AD. Now we're going to analyze numerous inequalities, including this first one here. Notice the sine of an angle is actually less than theta, and that is because theta can be represented by this arc length right here. Well, theta is non-zero, so if you divide each part of this inequality by theta, we're going to get this new inequality right there. Now, if we say less than 1, we can certainly say less than or equal to 1 as long as the angles are small. And small here means less than pi over 2 radians. Since the measure of OA is 1, note that the angle theta is also represented as theta radians, is actually the arc BA. That is less than the measure of AD, and that is quite obvious. You can see that the arc of BA is less than measure of AD. Now, what is the measure of AD? Another way of writing that is simply writing tangent of theta. Tangent of theta is also sine of theta over cosine of theta, and so we now analyze this inequality as long as theta is less than pi over 2 radians. Multiply each part of this inequality by cosine of theta, and we get this. Now remember, theta is non-zero, so if you divide this part by theta and this part by theta, we're going to get the next inequality, and we already know this is less than or equal to 1 from the note above. Now we know that the limit as theta approaches 0 from the right-hand side of cosine of theta is equal to the limit as theta approaches 0 from the right-hand side of the constant function 1 is 1. By the squeeze theorem, notice this function is squeezed between these two, we could conclude that the limit as theta approaches 0 from the right of sine of theta over theta is 1. Since this is an even function, we could also conclude that the limit as theta approaches 0 from the left, this will also be 1. Therefore, we actually have the result, or the identity, that we could use to help us understand the derivative of sine of x and the derivative of cosine of x later on. To give yourself some practice with trigonometry and algebra, go ahead and prove this identity on your own. To prove an identity, you start with the left-hand side and try to show it is in fact equal to 1. Go ahead and do this exercise as well. Try to show that this expression, using algebra and trig and limit laws, try to show that this expression will eventually be equal to 0. Now, if you haven't done an identity in a long time, I could give you an example with the following. Why don't we discover what the derivative of sine of x is by actually looking at a proof of an identity? So we're going to start with the word proof. And now we're going to start with an expression. The expression that we're going to begin with is the derivative of sine of x. Now, by definition, if this is going to be a derivative, we're going to simplify the limit as h approaches 0 of the respective difference quotient. So I have to write the sine of x plus h minus the sine of x all over h. So if we could simplify this, we're hoping we will get a function of x. Now the rest of the substitutions is just involves your trigonometry experience. And of course, you're going to need some algebra along the way. Now, with calculus and limit laws, you want to think 2 steps ahead. So you want to know if the limit of this function here, if it exists or not. You want to know if this function here, does this function exist or not? Using the properties you just discovered, if you use this property here, along with this property, we do know that these limits are going to exist. And that is because h is our variable. If h is our variable, that means x will act as a constant. And this will simplify rather quickly. Since those limits do exist, we can now write this expression here, which is absolutely miraculous, absolutely beautiful. I mean, absolutely beautiful. Now, this first quantity is 0. So 0 times sine of x will get you 0. However, this here is 1. So what we're left with is a function of x. And that function is called cosine of x. Now we'll use the transitive property of equality to make a conclusion. We can now conclude that this first expression here is indeed this last expression as well. This is actually equal. And so that is how you prove an identity. What was the identity? The identity is now revealed. This was the identity, and so if you had to change this idea, instead of the word discover, what you end up is actually proving the identity. And a proof of this identity is right here. You would actually just encapsulate all these expressions and these 2 sentences, and you now have a proof of this very, very specific identity. Hopefully that gives you enough of a hint to prove these identities. You want to work with the left-hand side, work your way down, and eventually show that this will equal to 1.